Good morning all. In this video, we'll discuss about linear block codes. Let us see what is a channel coding technique. A channel coding technique is nothing but adding some check bit or redundant bit to the transmitted signal so that the error caused by the noisy channel can be easily rectified. The error control codings are nothing but adding some extra bits to the transmitted data so which will permit for error detection or correction at the receiver. So there are two types of method of error corrections techniques are available. First technique is forward error correction. So forward error correction is nothing but a coding will be designed in such a case that the error can be corrected at the receiver, but this type of forward error correction will be used for one-way transmission, example broadcasting a television signal of data, and two types of codes to coding techniques are available under forward error correction. The first one will be a block code and second type will be a convolutional code. Now let us see the second type of error correction. The second type is called as the error correction with a retransmission or automatic repeat request. So in ARQ method, a decoder will check the input sequence. When it detects any error, then the particular part of the sequence will be discarded and it will be asking for the retransmission of the sequence. So the transmitter then again retransmit the part of the sequence in which the error has occurred. So what is the objective of a channel coding technique? So the main objective is to have a capability to detect and correct errors and should able to encode the symbol in a fast and efficient way and to be able to decode the symbol in a fast and efficient way. Now let us see what you call by a block codes. A data which is grouped into a blocks of length k bits, or we'll be telling that k bits to be a message or a data word, where each data word will be coded into a block of length n bits code words. For example, if you're going to take a k bits as 3-bit message or data word, so we are going to convert the 3 bits into an n bit code word by adding some check bit or redundant bit to the codes. So we call that code to be a block code. So we normally name a block code to be n comma k block code, where n is a code word which you are going to transmit and k is a message bit. So q is nothing but the bit which is referred as a parity check bits, which is being added with a message bit and converted to a code word for transmission. Now let us see what you call by a linear block codes. As per the definition, a code is said to be linear if any two code words in the code can be added in modular to arithmetic to produce a third code word in the code. So when we can call a block code to be a systematic, so after the conversion, after the encoding process, if the information bits are comes present in the first, followed by the check bits, then we can call that block code to be a systematic block code word. So as I already mentioned in this video, we are going to see about a linear block code. So linear block codes are nothing but the sum of two code words will produce another code word, and how the linear block code will be expressed. Let us consider any code vector that is having M1 to MK message bits and C1 to CN be the check bits, then the code vector of a linear block code can be written as x is equal to M1, M2, M3. This is nothing but a message bit, followed by the message bit will be having a check bits. So altogether will generate a code vector, where Q is nothing but the number of redundant bits, that is C1, C2, C3 up to N. So these are the number of redundant bits we are going to add to the encoder. So how a code vector can be generated in a linear block code. So the code vector in a linear block code can be written as x is equal to m into c. So m is nothing but the message bits and c is nothing but the check vector which you are going to add to it. So the code vector can be represented as x is equal to m into g. That is, if you want to generate a code vector, the message vector has to be multiplied with the term G. G is nothing but it's called as a generator matrix. Now let us see how a generator matrix can be represented as. So that a generator matrix G can be represented as P and IK. P is nothing but the submatrix and it takes a dimension K by Q, where K is the number of message bits and Q is the number of check bits, and followed by the submatrix. It consists of an identity matrix. The identity matrix is indicated by IK, which is nothing but K by K matrix. So if you want to generate a check vector, then a check vector has to be, the message vector has to be multiplied with the parity submatrix vector. So we can expand that form as C1, C2, C3 to CQ. This represents the check vector which we are going to generate with the help of a input message vector and the submatrix. So by solving the above equation, the check vector, so the first, the M1, M2, M3 is a message bits which is being multiplied with the, so each column of a submatrix. So for example, the first check vector can be generated as C1 is equal to M1, it is being multiplied with the P11 and it is being modulo 2 added with the remaining bits. So the C1 is given by M1 P11 modulo 2 added with M2 is being multiplied with P21, etc. So likewise we can generate the remaining check bits. So next we'll see what is called by a parity check matrix. The parity check matrix will be used at the decoding section, and this H is used to check if the code word is a valid one or not, and with the help of a parity check matrix we can generate a generator matrix. And this parity check matrix will be indicated in a matrix form as identity matrix followed by the submatrix transpose. Now let us see one problem under the generation of code vector using a linear block code. So the problem is given by the generator matrix for a 6,3 block code is given below. Find all the code vectors of this code. So here 6,3 block code represents 6 is a n number of code words we are going to transmit, and 3 represent the message bits. So from the generator matrix, we are going to generate all the code vectors. So to generate a code vector, we need a message bits and then we need a submatrix. So first we have to determine the submatrix from the generator matrix. As I already mentioned, the generator matrix will be consist of an identity matrix which is being given by 100, 010 and 001. Followed by that we'll be having a submatrix where the submatrix P is given by 011, 101 and 110. So from the generator matrix, first we are determining the what is the submatrix, and submatrix is given by K by Q, that is K represents number of messages and Q represents number of check bits present in it. So to obtain the equation for the check bits, here from the problem it represents K is nothing but, and the number of message bits given is 3, and number of check bits we are going to generate is going to be 3, and total number of code words bits are n is equal to 6. So here the block size of the message vector is going to be 3 bits. Since it is going to be a 3 bits, so 2 power k will give 8 message vectors which has been represented in the table. The message vector M1, M2, M3 which represents 8 message vector. So we are going to generate using this message vector, we are going to generate the check bits which will give the total n size. So the check vector can be given by the term C1, C2, C3 will be equal to M1, M2, M3 because we have 3 message bits. K takes the value 3. So M1, M2, M3 followed by that will be using a submatrix to generate the check bits C1, C2, C3. So the first check bit will be generated as M1 multiplied with the 0, and it is then modulo 2 added with the remaining 2 bits. M2 is multiplied with 1 and M3 is multiplied with the 1. So M1, M2, M3 has been multiplied and modulo 2 added with the first column of your submatrix, and then the check bit C2 can be generated by multiplying the message bit with the second column of the submatrix, And the check bit C3 can be generated by multiplying the message with the third column of our submatrix. See, if we look at the first equation, C1 is given by M1 into 0, that is modulo 2 added with M2 modulo 2 added with M3. So the first M1 into 0 will become 0. So we'll be getting the code as M2 modulo 2 added with M3, and C2, that is check bit 2, will give M1 modulo 2 added with M3, and the check bit 3 will be given as M1 modulo 2 added with M2. So let us see this one, how a code vector can be generated for the message bit 000. So for the message bit 000, that is M1 is 0, M2 is 0, and M3. So the check bit C1 can be generated as M2 modulo addition with M3, which we already got the equation. So 0 modulo 2 with 0 will give 0. And C2 M1 modulo M3. So 0 will give again 0, and C3 M1 modulo added with M2, again it will give 0. So for the message bit 000, the check bit which has been generated is also given by 000. So the message bit followed by the check bit will generate the code vector. Similarly, the second example takes, for the message bit 001, we got the check bit codes as 110. So likewise, we are going to generate the check bits for the 8 message vectors as shown in the table. So for the first one, 000, we got the check bit as 000, and for 001, 110, and for 010, we'll take example 010. For 010, the C1 is given by M2 modulo 2 added with M3. So M2 with M3, 10 will give 1 bit. Then C2 is 1, M1 modulo added with M3, that is M1 is 0, M3 is 0. 00 will give 0, and M1 with M2, again 01 will give 0. So likewise, we are going to generate the check bits for the 8 message vectors. So the message vector followed by the check bits will give the complete code vector, which is being represented here as M1, M2, M3, C1, C2, C3. As I already mentioned, since your message vector has been followed by the check bits are followed by the message vector, this is a systematic code block codes. Okay, learners, and next video we'll see another problem, how to detect an error, to correct the errors using a linear block coding method. Thank you.